So torque, you can think of torque like a force. Torque is what we would refer to as a rotational force. And it's going to be around or about some axis of rotation. Okay, so it's a rotational force around some axis of rotation. So yesterday, as you did the lab, even though the forces were not equal, the torques were equal to each other. The two torques were equal to each other. And in a seesaw, let's go back to the picture here. You have your little seesaw here. So even though, like if you're standing over here, even though it looks like there's not, it's not rotational, it's not going in a circle, if you would think about it, so it just looks like it's going down. But if we were to allow this to continue, let's imagine, for example, we put this on like a pin needle, and we just give it a little touch, how would it move? It would move in a circle, right? It would move just like a propeller. It would move around in a circle like this. So we're just looking at a tiny part of it, but it is arc-shaped. It is actually moving in a circle this way. And same thing if we put Dad right here, right? He would go in a circle this way if he were allowed to continue. And so even though the forces are clearly different, the torques are in balance. And so the torque going this way and the torque going this way, the rotational force, are balanced out together. And so there's no net torque, and we're in a state of equilibrium. Okay? So let's go ahead and define, or kind of define mathematically what torque would be. So the symbol for torque we use is a script T called tau. And you almost derived the equation yesterday. So one factor you clearly saw was the distance, right? The distance from the, in this case, the fulcrum, but the axis of rotation, that would be our distance d. And then yesterday when you did it, it was, you found the mass, right? You said it was md, but it's a force. It's a rotational force. So really what we should be using is not the m, but the force. And how much force would I be pushing down this way?
Force of gravity.
The force of gravity, right? Or the mass times gravity. So that would be the force that I would be pushing this way. So a torque really is not the mass times distance, but the force times distance, with the forces times distance. Okay, so that's going to be our equation for torque, F times d. We actually usually don't use d like maybe you used yesterday. We typically use r instead. And why would you use r? Because, yeah, it's a rotation, it's a circle. Ultimately, this would be a circle. And so we call this, we'd use r. If you want to stick with d, though, that's okay. But r would be that, you know, formally on your equation sheet, they're going to use r here. Okay, that's going to be our torque. All right, so let's look at some concepts of this. Let's look at, say, a wrench, for example. Let's look at some common things that you might use from time to time. Let's look at a wrench. So here's a wrench. Thing like this. Okay. So here's a wrench, right? Here we go. There's our wrench. That's what my pictures looks like. So anyways, so the purpose of a wrench is to essentially turn a bolt, right? We're trying to turn a bolt with our wrench. So there's like a bolt here. We want to turn it. So we're applying a torque on the bolt. We're trying to turn it in a circle. So we want to turn it that way. We're trying to turn it in a circle. So what do? Put a hand on it, we apply a force somewhere on the wrench. And one thing you'll notice about a wrench is typically, what's true about the handle of a wrench? It's long, right? You will never see a wrench that looks like this, a real short wrench. I guess you might see this, but it's not a good, well-made wrench. You won't see a real short wrench like this, right? And why is that? So if I apply a force, for example, here, or I apply a force over here, we'll call this F1 and we'll call this F2. In which case am I going to get more torque? F2, right? And so even though I'm pushing with the same force, I would never want to push my wrench like up close here to the handle. I would push it over here. And in fact, the farther away I push on it, the more torque I'm going to get, and therefore the easier it's going to be to turn the nut, the bolt here, right? Screw it to unbolt it. In fact, what if even here I was not strong enough to open this up? What might I do practically? Somehow make this longer. Okay, and one technique that people use is they'll put, say, a pipe on here. If they put a big long pipe like this, now all of a sudden if I've doubled the distance, I've doubled my torque, I've doubled my rotational force, and hopefully at that point I can open it up. Okay, so that's the whole concept of torque. There is one more thing I want to clarify. Let's go back to our wrench here. What if on my wrench, instead of pushing here or here or here, what if I push like this? What will happen? Okay, nothing would happen. Yeah, it would just push against the bolt. It wouldn't rotate at all, and I would never, ever, ever be able to unscrew this, okay, or unbolt it, right? So let's go back to our equation. So notice, what's the difference between this force and this force? The direction of the force, right? And so in our equation here, instead of writing force times distance, we're going to clarify this and say force perpendicular to distance, or force perpendicular to the radius here. Okay? Because if it was parallel, then nothing would happen. There would be no rotation. And if you pulled, say, at an angle, or pushed at an angle, which one's going to be easier, pushing at an angle or pushing perpendicular? Perpendicular, right? You're going to get more torque out of that if you go perpendicular. Okay, so this would be the equation that we'd use. What are the units here? So units for force? Newtons. And R, or distance? Meters. It's the Newton meter. That would be the units that we use for torque, Newton meters. Okay. By the way, this equation should look kind of familiar. We've had an equation of force times distance before. That's work. Yeah, but what's the difference? What was work? Force parallel to distance. And this is now force perpendicular. Okay? Alright, let's just do one real quick problem here. Let's go back to our wrench. I'm just going to redraw this. Alright, so let's say I'm going to push on my wrench. Let's say this distance from here to our axis of rotation is 30 centimeters. Let's say I push with a force of 20 newtons. Okay, let's say my son's going to help me out. He's going to push with the force at an angle though. Let's say 5 newtons. Let's say this is 10 centimeters away. He's going to push at 30 degrees. Okay, so can you find for me what is the, let's say, the individual torques? And then the net torque. Alright, so we have two torques exerted on this wrench here. We're going to try to open up a bolt, for example. We want to know what's the individual torque and then what's the net torque. So you're just going to find the two torques individually. So this one is going to be 20 newtons pushing this way. It is perpendicular. 30 centimeters going this way. So we'll call this torque 1. It's just going to be 20 newtons times, you do want to convert this. This should be in meters, not centimeters. So 20 times 0.3. Okay, which gives us how much? 6.67 Newton meters. Oh, just 6. 6.00 Newton meters. Torque 2. Alright, so this one, it's at an angle, right? So whenever you have things at vectors at angles, you can say, well, part of the force is this way vertical, part of the force is this way horizontal. So we'll call this Fy, we'll call this Fx, and which of those forces do we care about? Fy. So we care about the one that's perpendicular in this case. So when we find the torque, we're going to use Fy. Is this sine or cosine when we do it? Sine. So this is going to be 5 sine 30 times 0.1. Okay, what's the net torque on this? 0.25. Okay, 0.25 Newton meters. Alright, and then to find torque net, what are we going to do? Well, since they're in the same direction, they're going to add together, right? My son's helping me out here. He's going to increase the torque by pushing on it in the same direction. So we just add them up, right? 625 Newton meters. Now it is important to specify the direction. And for torques, we usually specify direction by clockwise or counterclockwise. And so in this case, what direction is it? Counterclockwise. So we're both pushing this way, so that's a counterclockwise direction.